Hello, everyone. Welcome to this second lecture in this series on inorganic chemistry. Specifically, we're talking about the trends in physical properties in period three. Period three, as you know, is from sodium through argon, that is 18 elements. So we've already seen about the variation in atomic radius, and we've seen that generally speaking, atomic radius does decrease across the period, though argon seems to escape the trend, and we've seen in laboratory as to why that is so. So continuing with that, the second physical property that we're going to talk about is the variation in ionic radius. Okay, now the variation in ionic radius kind of follows the same reasons as the variation in atomic radius, but the data looks slightly different. It looks as if there are like two sets of data. So variation of ionic radius. Okay, so allow me to get that big. All right. So variation in ionic radius. Now, the reason why I say that it looks like we have two sets of data is because the there are two types of two sets of ions that are being formed uh, across the period, right? So if you have sodium, yeah, magnesium, aluminium, silicon, phosphorus, sulfur, and chlorine, sodium forms the Na+1 ion, the Mg+2 ion, the Al+3, the Si+4, the P-3, the phosphide ion, the sulfide, and the chloride ion, right? And the chloride ion. So as you can see, there are two distinct sets of ions. You got the anions for the first four elements, sodium, magnesium, aluminum, silicon, while the next three are forming, the first four are cations, the next three are anions. Now, why would there be a big difference between them? Okay, just give me a minute. Let me just get the charges, everything. Because if you look at this, the number of electrons, you got 11 protons, 12 protons, 13 protons, 14 protons, 15, 16, and 17. But we look at the electrons, the cations all have 10 electrons. Remember, they lost electrons to become cations. All right? So all of them have only 10 electrons. The sodium lost 1, magnesium lost 2, aluminum 3, and silicon 4. They all have only 10 electrons. While the anions gained electrons. All right? So they will all have 18 electrons. Now silicon gains 3. Yeah. Sulfur gains 2. And chlorine gains 1. Now that basically means the cations have one shell less than the anions. So we say generally, or rather we can just say the cations of period 3 are smaller than the anions. This is because the cations have one less shell compared to the anions. And so the valence electrons are in the cations rather, are attracted most strongly as they have less shielding effect. So it's not just about the shell itself being closer, the valence shell itself is being closer to the nucleus, but it, there is also the added factor of the shielding effect coming into play. Okay. The valence shell for the anions is a third shell, so there are two inner shells shielding it, while the valence shell for the cations is the second shell, so there's basically one inner shell shielding it. So that is one. Now, among anions or among cations, let's start with cations first. Among cations, the ionic radius decreases across the period. All right, decreases across the period. Now, in the earlier discussion, we said that the atomic radius is the distance from the nucleus to the valence electron in the atom. Similarly, in the ionic radius, it is the distance from the nucleus to the valence electron in the ion. All right. Now, because you basically have all four of them having 10 electrons, you call them as isoelectronic species. Right? Iso means the same. So they're called isoelectronic species. We say the cations are isoelectronic, and as we go across the period, the effective nuclear charge, okay, the effective nuclear charge increases. Now you must be wondering, what is this effective nuclear charge? The calculation of the effective nuclear charge is a little complex, okay, and it is way out of our level right now. But for simplicity's sake, you can just consider that the effective nuclear charge is nothing but the ratio between the protons and the electrons. So it's the proton to electron ratio. Okay, so it's nothing but just the proton to electron ratio. All right, the actual calculation involves charges and the radius all put together. But for us, we can just consider that as the proton to electron ratio. All right, increases. Now, if you look at it, in sodium, there are 10 electrons, all right? In sodium, there are 10 electrons being attracted by 11 protons. So the proton to electron ratio is basically 1.1. That is the same as saying that each proton feels the attraction of 1.1 protons, right? So for magnesium, the same ratio becomes 1.2 because it's 12 divided by 10. So 11 protons attracting 10 electrons. But when you come to magnesium, the same 10 electrons being attracted by 12 protons. In aluminium, the same 10 electrons being attracted by 13, and in silicon, the same 10 electrons being attracted by 14 protons. So you find that the attraction just keeps increasing. And that basically means that the electron is going to be pulled a little closer because it's being attracted more. Okay, so we could have basically done the same discussion, similar to how we discussed atomic radius, but considering that they are isoelectronic species, we use a very simple approach by talking about the proton to electron ratio. So usually you tend to use the proton to electron ratio only in isoelectronic species because there everything else kind of remains the same, and the only thing that is varying is the proton to electron ratio. All right? So we reserve this for isoelectronic species. So we say that the cations are isoelectronic, and as you go across the period, the effective nuclear charge, which is the proton to electron ratio, increases. So valence electron is attracted most strongly and pulled in closer. When the electron is pulled in closer, we find that the distance decreases, so the radius decreases. Now, the same trend is observed in the case of anions also. Okay, a word of caution over here. Now, I've said that the same trend is found in anions also, but obviously you're not going to get any marks if you write the same trend is found in observed in anions also. So please make it a point that you repeat everything that you've done for the cation and for the anion as well. Okay. Now, if you look at the graph. Oh, by the way, if you notice, we did not speak about argon at all because argon, as we know, is an inert gas. It does not form any ion, so there's no point in talking about an ion that does not exist. I cannot say that it does not exist, but under what normal discussions we are seeing, the argon forming ions is just not. Okay. So if I look at the ionic radius, okay, so let's say that is sodium, say that is magnesium, aluminum, silicon. Again, I'm not saying that this is the exact graph. It is more of a trend line that we are trying to do. You find that the size of the cations keeps decreasing as you go across the period. All right. And the thing is, the size of the anions also decreases as you go across the period. All right. The size of the anions also decreases across the period. But take care to note that if you look at the largest cation, which is sodium, and if I, let's say I draw an equivalent line, the largest cation is still smaller than the smallest anion. So, I mean, this cannot be over here and this over here. I mean, this is wrong. Okay, this is wrong. So you need to basically ensure that the smallest anion is still bigger than the largest cation. Okay, so that is always something that is checked and where students usually leave marks. So please take care of that. And once that's that, we're done with this trend. And if you want, you can actually show this. And there it is. The trend in ionic radius across the